Hey everyone, today we're going over LeetCode problem 70, climbing stairs. This is another problem of the Blend 75 list, which is a list of problems commonly asked during technical interviews. In this problem, we are imagining that we are climbing a staircase, and we have n steps to reach the top. What we know is that we can either climb 1 or 2 steps at a time, and we want to return in how many distinct ways we can reach the top. We have here an example, and we are given n equals 2. This means that we have 2 steps in our staircase, and we see that our solution, our output, is 2. In fact, if we consider these 2 stairs, what we could do is climb 1 step at a time, so we would climb 1 step to reach the first step, and then an additional step to reach the top, or we could climb directly from step 0, the bottom, to the second step by using a 2-step jump. So we have 2 different approaches to reach the top, and therefore we return 2. Let's now consider this example where we have 3 stairs. One case would be to climb 1 step at a time. We could also decide to instead make our first jump a 2-step jump, and then following this have a 1-step jump. And our third scenario would be to have a 1-step jump initially, but then a 2-step jump. Each of these 3 different cases allow us to reach the top, and therefore in this case we return 3. The brute force to solving this problem would be to use decision trees. In a decision tree, we have a root node, which in our case will be 0 because we are starting from the 0th step or the bottom of the staircase. From this step, we know that we can make a 1-step jump, leading us to stair 1, or we can make a 2-step jump, leading us to stair number 2. Then from each of these respective nodes, we know that we can in addition decide to make a 1-step jump or a 2-step jump. And this allows us to create our entire decision tree. When finishing our decision tree, we see that we have many different paths in order to reach step number 4, which is the top of our staircase in this example. In fact, we see that our input is 4. If we count these 4s, we see that we have 5 different approaches in order to reach the top of the stairs, and therefore we return an output of 5. The time complexity using a decision tree is, in this case, is 2 to the n. And this is because for each of our nodes, we have a decision between jumping 1 step or jumping 2 steps. And because for each node, we have 2 different decisions we can make, we have a time complexity of 2 to the n. However, if we analyze this decision tree closely, we see that there are some subtrees which are actually identical. In fact, if we consider the subtrees which have 2 as their root, we see that there are 2. We have this subtree which has 2 as its root, but we also have this subtree which has 2 as its root. And if we look at these 2 trees, we see that they're identical, and this means that we're doing repeated work in this subtree. Therefore, we can use dynamic programming in order to take advantage of the fact that we have repeated subproblems and store the solution for these smaller subproblems in order to reach the solution of the larger subproblem composed of these smaller ones more efficiently. This dynamic programming solution will allow us to reach the solution in a linear time complexity. Let's once again see how many ways we can reach the top in a 4-step staircase. We have already seen the cases with 2 steps and 3 steps, and we have seen that these respectively have an output of 2 and 3. Now when considering how we can reach the 4th step, we know that this 4th step can be reached from the 3rd step if we make a 1-step jump, but it can also be reached from the 2nd step if we make a 2-step jump. Now because this 4th step can only be reached from the 3rd step or from the 2nd step, the amount of ways in which we can reach the 4th step is actually equal to the amount of ways we can reach the 3rd step plus the amount of ways we can reach the 2nd step. And since 3 plus 2 is equal to 5, we can return 5 for this case. And we also saw, using our decision tree, that this is the result we obtained with an input of 4. However, this is a much more efficient approach because this is a linear time complexity algorithm. And I'm going to show you how this is going to work. What we could do is use an array which will store the solutions for the preceding smaller subproblems and use these solutions in order to compute the solutions for the subsequent larger subproblems. Now let's now consider the case where we have 5 steps, and we know that we have 3 base cases, when we have 0, 1, or 2 steps. In fact, when we have 0 steps, there are no steps to climb, so we return 0. When we have 1 step, we can only climb that 1 step with a 1-step jump, so we return 1. And if we have 2 steps, we know that we can reach the top in 2 different approaches. Now when considering the 3rd step, we know that this can be reached from the 2nd step or from the 1st step. And when summing these 2 prior solutions, we get 3 as the solution for our 3-step staircase. Then we would move along in our array and consider the 4-step staircase. We know that the 4th step can be reached from the 3rd step or from the 2nd step. Again, we sum the 2 preceding solutions and we get 5 as our solution. Finally, we consider step 5. We know that step 5 can be reached from step 4 or from step 3 with a 2-step jump. We sum the 2 preceding solutions, 5 and 3, and we get a solution of 8, which we return. As mentioned prior, this algorithm is a linear time complexity algorithm, which is the most efficient we can get to for this problem. However, we can actually optimize this solution even more when it comes to space complexity. In fact, we don't need an entire array. We only need 3 variables in order to store information regarding our current step that we are currently trying to solve, our preceding step, and the step that comes 2 steps prior. We could call these step 1, step 2, and current step, and we would use step 1 and step 2 in order to find a solution for current step, and then move these 3 variables along to find the next solution. This solution, in addition to being linear in time complexity, it is constant in space complexity. We're going to start off our algorithm by taking care of our base cases, where we have 1 step or 2 steps. When we have 1 step, we know that we want to return 1 because there's only one way to reach the top. And if we have 2 steps, we want to return 2. Now we want to prepare our variables for our 1st step, our 2nd step, and our current step. So we know our 1st step will initially have a solution of 1. Our 2nd step will have a solution of 2. And then we're going to have our current step variable, which will initially be set to 0. And we know that in our picture, we have 1st step as our first variable, followed by 2nd step, and then current step is the solution of the step that we are currently trying to find. Now we're going to start a for loop, and this for loop will go from 3 because we're starting from the 3rd step, and this will go on until n, including n. So I'm going to put n plus 1 here. Then we're going to find current step as the sum of the solutions for the 1st step plus the 2nd step. Our 1st step is then going to be moved up to the 2nd step, and our 2nd step is going to be moved up to our current step. After finishing the for loop, we can just return 2nd step, or we could even return current step, as they are the same at this point. Let's make sure this runs. And we see that it works efficiently. Thank you so much for watching this video. If you enjoyed it, please subscribe to my channel. I'll see you on the next one.